And welcome back to Statistics 479 Time Series Analysis. Today we're going to be doing, the same thing we've been doing for the AR process, but we're going to be doing it for the ARMA process. I'm talking about estimation, forecasting. It's going to be a pretty good lecture. So when dealing with the ARMA process, we're going to be using the same types of tools that we were doing for the AR process. Specifically, we're going to be using maximum likelihood. Now, maximum likelihood is a good friend of ours, but it's going to require a strong assumption, and that assumption is that our white noise is Gaussian. Not a unreasonable assumption, but it's something to take into account nevertheless. Now, going forward, we're going to find that the equations are quite messy. So we're not going to go into them in excruciating detail. I'm going to try to spare you some of the nitty-gritty details, and we're going to try to focus on the big picture, what's going on, because ultimately there's going to be a function in R that's going to fit these models for you, but it's good to know what they're actually doing, what these functions, that is, are actually doing when you try to plug your own data in. And that's what we'll be talking about in this lecture.
And we're here again with another lecture of Statistics 479 Time Series Analysis. Today we're going to do, in some sense, exactly what we did before. But before, what did we do? We looked at estimation and forecasting for the AR process, the autoregressive process. Today, what we're going to do is do the same thing, but for the ARMA process. So now we're going to include an MA piece in our model. It's going to complicate things a little bit, but ultimately the main ideas are still going to be the same. We don't have access to the Euler-Walker equations because of the MA piece, but what we do have is we still have our good friend maximum likelihood, which we can work with, assuming, of course, that the white noise process is Gaussian. If the white noise is not Gaussian, the ARMA process is not Gaussian, and then we can't use maximum likelihood. Luckily, most things are Gaussian, so we're kind of okay as long as we're just aware of the fact that if we have a process whose noise looks very skewed in one direction, very heavy-tailed, very strange behavior like that, then we have to be a little bit careful when we use one of these methods to fit an ARMA model to our data. And this is really the same thing that you would do in linear regression, right? I mean, linear regression, as we would teach it at the undergrad level, has a lot of very strict requirements. If your data doesn't fit those requirements, you have to be a little bit more careful and try maybe more sophisticated methods. But at least for today, we're going to assume that all noise is Gaussian, and we're going to start to estimate some parameters for an ARMA process. So how do we do that? Well, let's go check out the notes and see. All right, so the first topic of today's lecture is going to be estimation for ARMA, PQ. So again, the idea that we're going to do is we're going to specify a P, specify a Q, and then try to estimate the parameters phi 1 through P, theta 1 through Q, the mean, the variance. In fact, I'll just write it all down, right? What we're trying to get is we want to be able to estimate the mean, mu, the variant, sigma squared, the autoregressive parameters phi 1 through phi p, and the moving average parameters theta 1 through theta q. So we actually have a lot of parameters that we have to worry about fitting. Even if p and q are not too big, there's still a lot of different things we have to estimate. And as I mentioned, what we're going to do is we're going to do this via maximum likelihood. So ultimately, we want to do the same thing we did with maximum likelihood in the case of the autoregressive process. So if we take a maximum likelihood approach to estimation, what we really just want to do is write down the likelihood of mu of theta, or sigma squared, of the phi's, which I'm just going to write phi because I don't really want to write lots of phi's, and the same with theta. So we want to write down the likelihood. Now, the joint likelihood is going to be a big multivariate Gaussian distribution. I don't know what that is. So instead, what we're going to do is we're going to use the same type of conditioning argument that we did in the autoregressive section of estimation. That is, what we're going to do is instead of writing the joint density function, we're going to write a product t from 1 to capital T of f xt conditioned on all of the previous measurements. Now this is basically, this is conditioning on all past observations. So in the AR case, we only had to condition back as far as the order of the process. If we had an ARP process, we only had to go P time units back. But we have an MA process now, or we have an ARMA, but we have an MA piece. And the MA piece is going to require us to condition all the way back through time, all the way back to X1. So we have a little bit of a more complicated conditioning here, but we're still allowed to decompose our joint density into the product of conditional densities. And that's what we're doing here. And all of these densities F are going to be Gaussian. All right, so another thing is assume, as always, xt is, I guess, causal and invertible for the AR and the MA piece, respectively. As I mentioned in the previous lectures when we looked at these things, there are equivalent processes that will be non-causal or non-invertible and will give you the same behavior stochastically. You'll get the same looking data out, which is kind of a weird thing to think about. But this non-uniqueness issue is why we want to enforce that what we're estimating is going to be something that is causal and invertible, so that we're only estimating one thing. We don't have data that could be represented by two distinct models. We have data and it's going to be one specific model that we are going to estimate from it. So that's an important thing in statistics. The idea of identifiability does show up a lot in statistics. So given this, right, we can write xt as an infinite linear process. So I need a sum in there, or else it's not going to be infinite. I equals 0 to infinity of phi I w t minus I. Right, where phi I are going to be some coefficients depending on, psi. The pitchfork one is a psi. Okay, so this is psi I from 1 to infinity, where the psi's are going to depend on the phi's and the thetas, to keep my Greek in line. Anyway, yeah, so we can write it that way. We can write it in this infinite linear process, causal linear process form. And furthermore, what we have is that for the random variable, so this is kind of weird, but I'm going to write the random variable xt given xt minus 1 through x1. So this is a univariate random variable. I'm taking xt, I'm conditioning it on the past measurements. It's still going to be a random variable. So this thing is going to have a normal distribution, Gaussian distribution. The mean, yes. So I'll just write it on the next line, with mean being the prediction, the one step ahead prediction, which we denote as x hat t minus 1 and t. So this is the prediction. No, I didn't change my color. There we go. This is the prediction of xt from xt minus 1 through x1. So all it's really saying is that the mean value is going to be of our random variable is what we would predict it to be, right? And what's the variance? Well, the variance, we'll say with variance, and the variance in this case is going to be, well, we can just write it down. It's the expected value of the random variable xt here minus x hat t minus 1 squared. And this thing is the mean squared prediction error. So the variance of this random variable coincides with the mean squared prediction error, which we denoted in the previous lecture as p, with a t in the subscript and a t minus 1 in the superscript, saying that it's the mean squared prediction error for predicting time point t based on all of the previous time points, t minus 1, and into the past. Now, this is good because it means that if we have a Gaussian distribution, and if we know what the mean is, and we know what the variance is, we know the entire distribution. So what that means, what that means, therefore, the likelihood, which I'm just going to write as L right now because I don't really feel like writing all the parameters in there. So the likelihood, which was just to indicate up here, star, red star. There it is. So the likelihood, right, is just going to be the product now, t, from 1 to capital T of, well, what's it going to be? It's going to be, let's see if we can do this with the normal distribution. It's going to be 2 pi times the variance, which is the mean squared prediction error, t minus 1. This is all to the minus 1/2. And then there's going to be an exponential. And the exponential is going to be something like 1 over 2 times the variance, p t minus 1. And then we're going to have x, I guess. Yeah, I guess I need a variable. So we'll just say x or something. Or no, I guess it's xt minus its mean, which is x hat t minus 1 t squared. So that's what our likelihood is going to be. And the problem is we need to figure out, well, wait, what is the mean squared prediction error? Right, we want to eventually, the point is eventually what we want to do is we want to plug in all the values we get, all the things we have here, so that the likelihood is in terms of all of our parameters, mu, sigma squared, phi, and theta. And the idea is that then we can do what we normally do, which is take a log, take a derivative, find the maximum likelihood estimator by, well, maximizing the likelihood, right? Finding the estimator that maximizes the likelihood, to just say the same thing in a different order. So to do that, what we have to do is get the likelihood into a form that we can start taking derivatives of, partial derivatives of, to get what's going on here. So for the mean squared prediction error, well, we can start with the case where t is equal to 1. And in that case, we would have a p1, 0, which we're just going to call the variance of, I guess the variance, for the process, the variance of xt. It's stationary, so the variance, maybe xt is a little confusing because I said t is equal to 1. It's stationary, so the variance will be the same for all time points. I just need to write something there. So I could write x1, right, if I really wanted to. It's, this is equal to the variance of x1, etc. But what we can do is we can use this form of a causal linear process up above to note that since white noise is uncorrelated, And, well, actually, in this case, it's Gaussian, so it's independent white noise because it's Gaussian white noise. Furthermore, the psi coefficients have to decrease fast enough to make that thing absolutely convergent. So what that means is that I can write this out. Basically, I can flip the variance and the summation, and I get something that's going to look like sigma squared from the when I take the variance of those terms, the W's, the white noise, and I'm going to get a bunch of psi I squareds. So I can write down, at least in this case, what it would be, and psi is going to end up being a related to my parameters phi and theta. So then the question is, well, what happens when t is greater than 1? Well, from last lecture, t greater than 1, we can use what we learned about from Durbin-Levinson in the past lecture, which, if you recall from the past lecture, was something like, pt plus 1t is going to equal to the previous guy, pt minus 1t, times some updating, basically times some alpha coefficient. Something that looked like this. Now, as I kind of point out in my written notes, I'm not so concerned about the precise computation because all of this stuff is going to be kind of pushed under the rug in a second. But the idea that I want is that you intuitively understand what's going on here, not that you can go through and get out every nitty-gritty detail and partial derivative, because it's just not worth it to go through all of the individual details. It's kind of tedious and boring, and I don't think you really learn anything from it. But what I want to do is I want to give you the intuition about what we're actually doing here and how this is all coming together. So the idea is that we can write p t minus 1t, which again is the mean squared prediction error. It's the variance for our normal distribution. And what we're going to do is we're going to write it as something that's going to look like sigma squared times RT. Now, okay, we could figure out what RT is, but I don't really want to. The point is that RT does not depend on sigma squared. So is that clear? The idea is that we start with our first mean squared prediction error just being the variance, which is sigma squared times something else. Then when we update it using Durbin-Levinson, we just keep multiplying by some alpha, which is in terms of things that do not depend on sigma squared. So ultimately, we're going to have sigma squared times something, and that something is not going to depend on sigma squared. That's going to matter because, therefore, we get our likelihood once again, which I'm going to put that little red star to indicate that once again, we're back to writing down the likelihood. And every time we write it, it gets a little bit more intelligible. So in this case, what we're going to get, well, actually, we don't need that product because I'm going to take the product over everything. So inside the first thing in the product is a 2 pi and our variance term, or our mean squared prediction error term. So we're going to have a 2 pi. 2 pi is going to be multiplied by itself t times, or I should say 2 pi to the minus 1/2. And there's also going to be a sigma squared in there that's coming from the p. So what we end up with, the first thing we get, is a 2 pi sigma squared, and that's going to be to the minus capital T over 2, because I multiplied t of them, capital T of them together. So the other thing we're going to get are going to be these RTs, which I can keep as a term unto themselves. And that's going to look like T from 1 to capital T, RT, the minus 1/2. Yeah, because in this case, every RT is going to be different. We're just taking the product of all of them, but there still is a power of -1/2 from the Gaussian distribution. And then what we're left over with is something in the exponent, and that something in the exponent is going to be minus, and I'm going to write it as notation S mu phi theta divided by 2 sigma squared. So if you recall from when we did estimation for the AR process with maximum likelihood, we had this S term in the exponent. That was the conditional or the unconditional sum of squares, depending on which part of the lecture you're referring to. In this case, what we're going to have is that S of mu phi theta. Again, there's no sigma squared dependency here, which is going to be important when we start taking derivatives. So this is going to be the sum t from 1 to capital T of, well, this guy, xt minus x hat, xt minus x hat, t minus 1t. But there's one more thing in the denominator, which is that RT term, which is a little mysterious because I don't want to write it down because it's just a big mess of terms. It's not really pleasant to deal with, but the point is that it's still there. And this is what we have, some sort of sum of squares. I forgot the square. It's not a sum of squares if you don't square it. There we go. Words to live by. Anyway, now what we have is we have some type of sum of squares equation, and if we do the calculus that we've done multiple times already, then we can say ... via calculus, we get that the estimate, the maximum likelihood estimate for the variance for sigma, or the sigma squared, which is the variance of the white noise process. Remember, the variance of xt is up here. It's sigma squared times something else. But the sigma squared is the variance of the Gaussian white noise that is sort of, driving the time series, the ARMA process that we're working with. Now, yes, what were we doing? We were writing down the estimator, and we're going to get what we normally get whenever we try to estimate the variance of a Gaussian distribution using maximum likelihood. And what we're going to get is we're going to get the sum of squares, where we fill in the parameters with hats and we divide by n, right? This is more or less, it's a little bit maybe less clear in this case, but it's the same thing that you get every time you try to take the derivative of, or you try to find the maximum likelihood estimator for the variance of a Gaussian distribution. Sum of something squared divided by n. Sometimes we end up, subtracting one or more, or two, or p from n based on the number of parameters, but that's not the maximum likelihood estimator. That's the unbiased estimator. So in this case, we're just doing maximum likelihood. All right, so now what we would need to do is we would need to figure out what mu hat, the phi hat, remember phi hat and theta hat are just placeholders for phi 1 through phi p, theta 1 through theta p. So they're actually kind of vectors of parameters. So basically, yeah, now what we need to do is, yeah, that's right. Maximize the concentrated likelihood is a new term. So then we get something called the concentrated likelihood. Okay, so what is that? Well, what that's going to be is that we replace sigma squared above by S of mu phi theta over n. Because we kind of, again, this is one of those goofy things in math, right? It's like we know that there's a sigma squared hat and it exists and it's a thing and it depends on other parameters. I don't know what it is yet, but I can still work with it in the likelihood equation. And the neat thing is that if I plug that in, then, well, things become a little bit simpler. So we're going to write down the likelihood for the dot, 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 therefore, star likelihood equation. We're going to write it down another time. And now we're going to get a 2 pi. Our sigma squared here is going to be S mu phi theta. There's going to be a divided by n here. So let's increase the size of these parentheses and then take it to the minus t over 2 power. There's still going to be this RT thing here, which, yeah, it's kind of annoying, but it's just there. Minus 1/2. Then the interesting thing is what happens in the exponent, because in the exponent, what we'd be getting is we take our S mu phi theta and divide it by S of mu phi theta. So the whole thing cancels out and we're left with just an n over 2. So this is, I guess, not really L, it's the likelihood, it's the concentrated likelihood. We basically say, okay, we have an idea of what sigma squared should be, so we're just going to plug it in and push forward. And by doing that, now we're going to take the derivative, the partial derivative of this thing with respect to mu and phi and sigma squared in order to, well, find the estimators, that is we can solve for then the maximum likelihood estimators for everything else. So this means that we're going to get a log, that's not a very good log, we can do this, log likelihood, and the log likelihood in this case is going to be some coefficient c, which is all the junk depending on n and 2 pi that I just don't care about. And then we're going to have the stuff that we do care about, which is minus t over 2 times the log of, well here, except I'm doing one silly thing. I switched the sample size because, right, in statistics, very often we treat the sample size as denoted as lowercase n. In this case, our sample size is actually capital T. So, I mean, everywhere, I think I just started doing it down in the likelihood equation. Yeah, down here. So this guy should actually be a capital T. Just, it's the same thing, right? I'm dividing by the total sample size, but to be precise, the total sample size in time series world is capital T. So this should also be a capital T. And this guy here should be a capital T. Okay. So, yeah, besides that, we're all good. And then what we're going to get is we're going to get the log of S mu phi theta divided by capital T. I need to go back and make that more clear in my notes. And then we're going to take the derivative of this guy, well, not the derivative, sorry, the log, and we're going to have a minus 1/2 times the sum. All right, so where were we? Well, what we're going to do is we need to write down t from 1 to capital T of the log of RT. And this is going to be our log likelihood, which we can then take derivatives of and try to estimate the parameters, or I guess solve in some numeric sense on a computer. So, okay, I don't particularly want to do that because it would require us to write down all of these terrible terms. What I really want you to take away from this is just the intuition about what we're doing. So let me finish this statement and just say, then we can solve for mu hat, phi hat, and theta hat given all of these terms. I just want you to go through the thought process of what we did, right? What we did was we said, okay, we have xt. It has a normal distribution because we're assuming it's Gaussian process. I don't want to write down the joint density, so I write down the joint density as a product of conditional densities. Right. I know what the mean and the variance are in terms of the one step ahead predictor, and the one step ahead mean squared prediction error. So then what I have is my giant likelihood equation. What I need to do is plug in something for P. After I plug in something for P, now I know I can get that, right? If I plug everything into an algorithm, I can access all of the P's. It's just that in an equation sense, it's going to be really messy to write down. Then what I do is I come down here and I get my likelihood in a nice form where I have my sigma squared, the variance of the white noise, separated from all the other parameters. As often happens with a Gaussian distribution, I can get the estimator for sigma hat squared. And then the new trick, which might be something new, I mean, all of this so far is stuff that you would see if you just did maximum likelihood estimation for the normal distribution, the univariate normal in like Stats 101 class. It's just the notation is a little bit more terrible. But what's interesting then is this idea of concentrated likelihood, where you then plug this guy back into the likelihood to simplify the exponent and give yourself something to work with. And then from there, we just, I guess, brute force our way through and can get all of the parameters. Luckily, there are R packages that will just calculate this for you, but it's really good to know the thought process that goes into where these estimators are coming from and how they come about. And furthermore, what I think is more interesting to focus on is also the asymptotic properties of the estimators, because right in stats, we estimate things. The things we estimate very often are going to be asymptotically normal. It's kind of a like constant theme in all of statistics. Okay, I have data. I estimate a parameter. What's that parameter? It's normal enough. And sure enough, we get asymptotic normality in this case. So the next little section is going to be asymptotic normality. And this is important because asymptotic normality means that if our data size is large enough, our estimator should look normal. If we know what the mean and the variance should be, then we can do hypothesis tests and we can say, okay, is this parameter significantly different from 0? That is this actually a significant parameter in my model or not? We can do confidence intervals. We can say, okay, here's the AR parameter or the MA parameter that I computed, but where do I think the true parameter lies? Boom, 95% confidence interval brought to you by asymptotic normality. Though I've always been a more fan of the non-asymptotic approaches to statistics, but they're less popular, I guess, just because they're kind of newer. Well, more or less. Anyway, before I get off on a side tangent, let's denote beta to be a big parameter vector of phis, phi1 through phi p, and yes, theta 1 through theta p, or q, theta q. And we're going to denote, I'm going to write this in a different color, that if I put a hat on beta, I'm just putting a hat on all of the elements inside the vector. So we're going to have beta, which is the vector of true parameters, we're frequentist statistics at the moment. So we have true parameters for the model. And then we have beta hat. Beta hat is the vector of estimators for all of those parameters. So what are we getting? Well, we get, denote this, where, say where the hats indicate MLEs, maximum likelihood estimators, then that is the stuff that we would have gotten from up here if we solved all these, I guess, derivatives or optimized the maximized the likelihood with respect to all the parameters. Right, so then what we get is that the square root of t, the sample size, times beta hat minus beta, which is the difference of the two vectors, converges in distribution to a normal 0 sigma squared random variable with matrix gamma pq. I'll write that down in a second. This is as capital T goes to infinity. So another reason why I say in the project component of your course, I'd like you to make sure that the data size you have is big enough. Don't come with like a time series that has 15 observations, because we really want T to get big in order so that we can trust all of these estimators, or at least the normal approximation, the normal, the asymptotic normality of these estimators. Right? We're never asymptotic. We never have infinite data, but we have enough that we say, we're close enough to being infinite or asymptotic, I guess. I've never really liked that argument, but it is sort of standard practice, and it does actually work in practice, so you can't fault it too much. Anyway, I didn't tell you what that matrix gamma is. So the first point is that we have asymptotic normality. Hooray! We have an asymptotic normal distribution where gamma PQ is going to be, well, I'm not going to tell you exactly what it is yet. I'm just going to go one step further down the rabbit hole and tell you that this matrix is a block matrix in terms of what we'll call gamma phi phi, gamma phi theta, gamma theta phi, gamma theta theta. I wonder if there are any like frats or sororities that are gamma theta phi. If they are, they're must be into time series. So going forward, what are these matrices now? I'll say another where, iterative wheres here, where I'm going to say gamma phi phi ij. The ijth entry of that matrix is going to equal the autocovariance of y. I didn't tell you what y is yet, but I will in a second. I minus j, where capital phi b of y t is equal to wt. That is, yt is the AR piece of xt. So, okay, and we haven't told you what the other gamma matrices are yet, but let's stare at this for a second. What we're saying is the matrix gamma, the phi matrix gamma, is going to be a matrix of autocovariances. Again, as I mentioned, autocovariance is basically this entire course. And the autocovariances are not for x, they're for y. And what is y? Y is the process, is basically xt if we just deleted the moving average piece, right? I should point out here that we had, I didn't actually write this down at the beginning, but we would have something like this. theta B W T. Here, I guess I'm saying we'll say mean 0, so I don't have to put in a mean term and worry about messing that up. But that's what we have, right? We have our ARMA PQ process has two pieces to it. It has an autoregressive piece and a moving average piece. In this case, we're just looking at the autoregressive piece for that matrix. And as you might guess, for the other matrices, we're going to look at the for the other matrix, gamma theta theta, ij. The ijth entry of that is going to be denoted as k of y prime ij. So, okay, well, what's that? Well, where? We just have wheres all across the board here. Y prime t is going to be the moving average operator applied to wt. So this is the ma piece of xt. So that's what we're kind of doing here. And then I guess the last thing we need to figure out is what are those off diagonal block matrices. I guess we'll say that gamma phi theta ij is the cross covariance between y and y prime I minus j, and likewise the reverse of that, theta phi. It's symmetric, so you can just transpose it, but you can also write this as y prime y I minus j, even though they're the same thing, right? No, I have to transpose it together to work because it's going to be a p by q or q by p matrix. So besides the transpose, they're basically the same thing. Right, so that's the result. I think somewhere, possibly in the textbook, there's a nasty long proof of it, which we're not going to do in this course because I'd rather just spend the time explaining the concepts and then doing some examples in R. Though at this rate, we might be doing the examples in R probably in the next lecture once we talk about forecasting a bit in the latter half of today's lecture. But before we're done with this section on asymptotics, let's do a simple example, or two simple examples. So example 1, which is the AR1 process, which is, of course, just xt is going to be phi xt minus 1 plus wt. And with the variance, the auto covariance at lag 0 from many lectures ago, it always seems to pop up. It's going to be this thing. It's sigma squared, the variance of the white noise divided by 1 minus phi squared. So therefore, the point is that this gamma matrix above, this guy here in green, is going to be pretty simple because it's a 1, 0. So it's not even a matrix. It's just one single value. And what's that value? It's just, I feel like I need to, I think we need to divide all of these by sigma squared because we don't want the sigma squared being in here twice. See, make sure I'm not messing something up. I have my sigma squared in there. So I don't want a sigma squared to pop out of here. So in some sense, I guess I would need to divide all of these things by sigma squared so that I don't have two sigma squareds in my matrix. The point is that what I want here for this guy is just the 1 minus phi squared to the minus 1, but I don't want that sigma squared floating around. Therefore, what we get is we get that our estimator phi hat is going to converge. Let me double check this. Yes. Our estimator is going to converge in distribution to phi with, I'll just write it out and then we'll talk about it. I think we need a sigma squared in here. And a 1 minus phi squared. Yeah, that looks better. I think I forgot the sigma squared in my typed up notes for this lecture. So what we're saying is that, okay, this is good, right? We have our estimator here, and it's going to converge in distribution to the right, the thing we want, which is phi. And we have a variance which goes to 0 as t goes to infinity as we get more data. So the variance is also going to depend on 1 minus phi squared, which is quite interesting, because that means if phi is really close to 1, remember, it can't be 1 or else we have a random walk, it's not stationary, everything falls apart. But if it's close to 1, then it's going to shrink the variance by some constant. So the variance in some sense will be smaller as phi gets closer to 1, which is quite interesting. Whereas in some sense, the worst case scenario for the variance would be if phi is equal to 0, then the variance is just that of white noise, right? So that's another interesting thing to point out, because I was kind of mentioning this with the mean squared prediction error in the previous lecture, that I said, okay, the worst possible prediction error is just the variance of the white noise. And then if you're lucky, you can gain some information from previous observations and the prediction error will go down. Well, in this case, right, what we basically have is we have two pieces here for the variance. We have a sigma squared and we have a 1 minus phi squared. And when we look at these two things, we have the variance of WT, and this is the influence from the AR, I guess, 1 process. So it is kind of nice to look at these formula and kind of see what's going on here. So by symmetry, we actually get, well, I'm going to do another example. And by symmetry, it's actually just going to be the exact same thing. But we're going to write it out anyway, just to make sure it's clear. In this case, we're going to have our MA process, which is going to be theta WT minus 1 plus WT for theta less than 1, so it's invertible, etc. So what's going to happen here, and this is kind of funny, is that, well, first, the MA polynomial is what? It's going to be 1 minus theta, not 1 minus, 1 plus theta b. Oh, that is not how you write a polynomial. Theta of b is equal to 1 plus theta b. And that's kind of neat because, well, what we're ultimately going to do is then try to basically look at this as an AR process. So therefore, the AR1 model theta b applied to some time series y equal to WT has the same behavior as above, which means that we're going to get the exact same thing out, which in this case is just going to be, well, the same thing we had before, but I'm going to replace the phi's with a bunch of thetas. That needs to be a theta squared. Cool. So that's a kind of a little weird, tricky thing, but it's basically saying that, we get the same behavior in both cases of our estimators, at least for the AR1 and the MA1. And we see the same thing, which is the closer our parameter is to 0, theta or phi, the closer our process is to white noise. If theta or phi tend towards 1, I guess -1 as well, but let's say they tend towards 1, we start to move towards the random walk in the one case, or in the moving average case, I'd guess we'd be on this weird cusp between invertible and non-invertible. I actually don't know what that process would look like. That's a bit of a strange process. I haven't really thought about that one. But ultimately, what we're doing is we can kind of see how we move from something that's close to white noise to something that's, not close to white noise. And then the last question is, how do we pick P and Q when estimating an ARMA, or fitting, I should say. I mean, estimating the parameters, but when fitting an ARMA PQ to our data. So how do we choose the order P and Q? Well, there's a couple ways. One is we could just use something called auto.arima in the forecast package, which does it for you. But then the question is, well, then how does that function pick the P and the Q? And we can say, or ARIMA in, I think that's just in the stats package, the default one in R. And the point is we can use AIC or BIC for model selection. And that's exactly what that auto ARIMA does behind the scenes. It basically says, okay, I forget if it defaults to AIC or BIC, but whatever it defaults to, you can switch it to the other one. And it'll say, aha, I'm just going to fit a whole bunch of ARIMA models until I find the one that minimizes the AIC or the BIC or whatever you give it. And that's sort of, standard model selection type approach. You can do it manually using the ARIMA function in the stats package. You can fit a few models and then decide, well, which one has the smallest AIC or smallest BIC? That'll be my favorite, depending on if you like AIC or BIC. Even though very often they're probably going to give you the same answer, but not always. So you have to be a little careful. And you get to do that in your next assignment that you should be working on, and actually fit some ARIMA models to some actual time series data. So that's pretty neat. All right, and we have one more thing that we're going to start discussing in today's lecture and finish it in the next lecture, and that's forecasting for the ARMA process. We'll start it today, talk about some of the basics. We'll finish it up in the next lecture, and then we'll just look at some R code for fun, for estimating and for forecasting ARMA and ARIMA processes. So moving on, we're going to talk about forecasting for ARMA PQ. Right, so What are we doing? Well, let's just write it down. I forgot to write down the model last time, but we'll write down the model right here, just so we have it in the front of our head and somewhere on the the OneNote page so that I can point at it if I have to. So we're going to ignore the I part, the integrated part. It's not going to be an ARMA model, it'll just be an ARMA model, but you can do a lot of these things for ARMA models too. You just have to, account for the differencing. And we assume causal and invertible, as always, basically. So again, what we want to do is we want to predict, say, well, what we want is an H step ahead prediction. Very often we just do a 1 step ahead prediction, but okay, we can do H steps ahead. And what that's going to look like is it's going to be some estimator x hat t plus h. And it's really just going to be the expected value of, well, x. I was using capital T because we're saying our data set goes all the way to capital T. We want to predict h time units into the future. What is it going to be? Well, it's just going to be the expected value of that random variable conditioned on our entire data set. All right. But there's going to be a little twist we do here, and that's it's mathematically nicer to condition on infinite data. Okay, so we actually get a different term, which is going to be x tilde t plus h. And this is going to be, well, the expected value of xt plus h conditioned on x capital T back to x1, but we're not going to stop there. We're going to include an x0 and an x minus 1 and go off to the infinite past. Now, that data does not exist in our data set. We only have these t measurements, and we do not have any ones that go past that. What we're going to do is use x tilde to mathematically understand the forecasting, or the estimator, the predictor, I should say, the h step ahead predictor, and then we're going to switch tilde to hat at the very end. So stick with me here. It's pretend now that, okay, we have access to lots of data. And it's not completely terrible thing to think about, because as t, the data size, gets large, all of this stuff that I underlined in red becomes fairly negligible, and these two predictors become very close to each other. So again, we don't have the ability in the real world to work with x tilde because we don't have infinite data, but we can mathematically try to understand it, and that's what we're going to do. So the next thing we need is we need to write out our process both as a causal and an invertible process. So this is kind of, I guess, step 1 is get these things. Step 2 is we need to write out the causal and invertible process. So a causal linear process, going back to one of the first lectures, is going to be x t plus h is just going to be w t plus h plus an infinite sum j from 1 to infinity of psi j w capital T plus h minus j. And we're also going to have our invertible process. And in this case, we get not an x, but we have a wt plus h. And this will be a big sum of x's, xt plus h plus the sum j from 1 to infinity of pi, my new parameters, pi j, x capital T plus h minus j. Whew. All right, so we have this. This is something that we did back in, I think, chapter 1 of the lecture notes, but it's good to write it down because we're going to need these tools going forward. Mainly, we're going to apply this conditional expectation to these terms and see what happens. So now, combining 1 and 2, what we get, well, okay, we're almost at that point. First, note that the expected value of wt conditioned on capital or x capital T all the way to x0 and on to the infinite past. So this is, again, infinite past. Well, this, we know what this is. This is either going to be wt itself. This is if little t is less than or equal to capital T, or it's going to be 0 if little t is in the future. Okay, so why? Well, so why is this true? Well, for 1 point, if t is greater than t, if little t is greater than big T, as I like to say, the white noise lives in the future of our data. So it's basically more mathematically what we can say is that if this is true, then wt is independent. Yeah, I think we're still assuming Gaussian in this case. I guess, no, I'll say uncorrelated just to keep it as general. We don't actually, well, no, we're conditioning, so we do need independent. Yeah, so I guess we probably need to emphasize, I don't think I did that in this case we would need at least independent IID white noise. Of the past measurements, xt, all the way into the past. Again, this is because the process is causal, which means that it only depends, the x's only depend on the current time and the past. Wt lies in the future. It's independent of all of that stuff. And then 2, we say that if t is less than or equal to t, then we have a 1-to-1 correspondence between the x's and the w's, i.e., conditioning on xt going into the past is kind of equivalent to conditioning. This is terrible notation, by the way, but I hope it makes the point. Wt into the past, right? The xt is just a linear combination of xt's and wt's, so we can always just invert it somehow and say that if we know what every xt is from now into the infinite past, well, then we know what every wt is from now into the infinite past by just, I guess, reworking the equations. It's equivalent conditioning. So we have that. And then I'll say similarly, what we have is that, so this is, I guess, one thing we need, and the next thing we need is going to be that the expected value of xt, little x little t, conditioned on the entire infinite past, x capital T, through 0 and on to the past, well, it's going to be one of two things. If it's either just going to be itself, this is if t is less than or equal to capital T, and otherwise it's going to be x tilde, right? This is x tilde t if t is greater than capital T, right? Because that's exactly what we wrote down back in step 1. We said, well, in this case, we're just replacing capital T plus h with little t, but it's the same thing. Okay, we have that. Therefore, our causal representation becomes what? Well, I should say applying this to the causal representation, what we end up with is, where was that causal representation? I just have not quite enough room to fit it onto the same page, but that's okay. What we end up with is an x tilde t plus h is going to be the sum, in this case j, but we're not starting from 0, we're starting from h and going to infinity of psi j w capital T plus h minus j. Okay, so what happened there? This is after taking the conditional expectation of each side. So let's look to make sure we know where that came from. Up here, my causal representation, I have an xt plus h. If I take the expected value of xt plus h conditioned on the data, I get an x tilde t plus h. On the right-hand side, if I take a conditional expectation of each of these w's with respect to the data, I either get the w or I get a 0. So what happens is, the first, I guess, h minus 1, well, h from 0 to h minus, or the indices from 0 to h minus 1 of the w's all vanish, because when I take the expected value, they become 0. They lie in the future of our data set, and the only thing that remains are the w's and the phi's for j from h onward. This is why it's really convenient to be able to condition on the entire data in some infinite analog of our data set. All right, then as we fight our way through this, remember what we're doing. We're trying to do prediction here. We're trying to understand what this predictor is. So then we end up with the fact that x t plus h, the thing that we're trying to understand, minus x tilde t plus h, the predictor of mathematical convenience. If we subtract one from the other, we get a finite sum, and that is quite nice, actually. I like finite sums. J from 0 to h minus 1 of phi j w t plus h minus j. And that means we can write down the mean squared prediction error. The mean squared prediction error, or using that p notation that we were using in the last lecture and earlier in this lecture, if we want the mean squared prediction error for t plus h given the data from t into the infinite past, again, we're still doing infinite past here because it's mathematically nicer. Well, that's just the expected value of this thing, xt plus h minus x tilde, t plus h squared, i.e. it's this thing squared, and that's just going to be sigma squared, as is always out front, the sum j from 0 to h minus 1 times the psi j squared. And it's a finite summation, so that's great. We don't even have to, it is causal, so we know that the infinite sum would have to converge, but we don't even have to worry about that in this case. All right, so that was the causal representation, looking at the invertible representation. There was a reason why I wrote down both of them. Well, we can do the exact same thing, right? All I did up here was apply the conditional expectation to the causal representation. If I do the same thing for the invertible representation, what we find out is that we get a 0 because, I should just write it all out. The invertible representation is a WT, and let's go find it. Yeah, xt plus h and then a bunch of pi's is equal to x t plus h plus the sum j from 1 to infinity of pi j x t, capital T, plus h minus j. So what happens is when I apply the conditional expectation here to both sides of this equation, well, I get a 0 because I guess t, well, I shouldn't use t, capital T plus h lies in the future of the data set. And then I'm going to get my x tilde here when I take the conditional expectation of that term. And then we're going to get two things out here. We're going to get a j from 1 to, I think it's h minus 1, pi j x tilde t plus h minus j, plus the sum j from h to infinity of pi j x t plus h minus j. So anything that has an index that's greater than capital T gets a tilde stuck on top of it. Otherwise, we just keep the series the same as before because we're conditioning on the data points that we are just looking at. Therefore, what we have is that the predicted value x tilde t plus h depends on the data xt going into the infinite past and the previous h, is it h or h minus 1? I think it's h minus 1, yeah. H minus 1 predicted values. So what that means is that if we want to predict the h, I can't put a th after h, just doesn't work. If we want to predict the h time points into the future, we'd start by, well, predicting 1, and then 2, and then 3, and then 4, and then so on up to h, which makes sense because so often in time series we have things like autoregressive processes where the previous observations tell us what happens in the next case, and that's what's happening here. All right. Yeah, we have a little bit more time. So what I'm going to talk about is we're just going to finish up our discussion on x tilde today, and we're going to leave the figuring out how to turn x tilde into x hat for the next lecture. But we're not quite done yet because I want us to talk about what happens when we try to predict far into the future. I feel like I should go into like an audio editor and have like future, but that would just be silly. So we're not going to do it. But it is an interesting point, right? In time series, we're often trying to predict future measurements. We want to know what the price of our stock's going to do. We want to know what the what the number of COVID cases is going to do. We want to know what the global temperatures are going to do. Hopefully, they're not all going to go up, except for our stocks, of course. We want those to go up. But the other two, let's have them not go up. But the thing is, how far ahead can we actually feasibly predict in a time series? Because time series are super noisy. So does it even make sense to predict that far into the future? Well, you can. And we can figure out mathematically what we'll get out. So, yes, what we need to know is a couple things. Well, first of all, what we have our predictor. Well, what I'm going to do is I'm going to write out X. I'm going to write out the causal one, which has fallen off the top of the page once again. J from h to infinity of psi j w t plus, not t, capital T plus h minus j. So that's our causal representation, where we know that the sum j from 0 to infinity of the absolute value of the phi j has to be finite. This came up back in, I think, one of the first lectures where we talked about a causal linear process, that the coefficients have to be absolutely summable. Okay. But that's actually quite interesting because therefore, well, there's a couple things. We know that phi j has to go to 0 as j goes to infinity. I mean, yeah, if it's summable, if it's absolutely summable, the terms, the coefficients, the things, the summands, I guess is the word I'm looking for, have to go to 0. But there's something else that's even more interesting, and that's the sum of j h to infinity of the absolute value of phi j has to go to 0 as h goes to infinity. And this is what we call a tail sum, right? If we only sum, if we start our summation at h instead of 0, well, it's going to be slightly smaller. As we push h to infinity, this thing also has to go to 0. So what does that mean? Well, therefore, let's bring this guy down here. And what it tells us is that x hat t plus h is going to tend towards the mean mu as h goes to infinity. So as we predict further and further into the future, what are we predicting? We're predicting the mean. We're saying I have a stationary process. It has mean mu. If I watch this process for, years and years and years, what's the best prediction I have? It's the mean, right? That's all we have to work with. Because it's kind of saying it could fluctuate up, it could fluctuate down, but on average, we know what it's going to be. And yeah, I guess actually I should be more precise. This is convergence and probability. We have that by showing that the variance, actually goes to 0. I wonder if you can show that it's almost sure convergence. That's just sort of mathematical fun, but yeah, that's always a harder thing. You always have to show that it actually converges, but in a fast enough way to become almost sure. But we don't really need that. I'm just going to skip ahead and say that and the mean squared prediction error is p t plus h And that's going to be sigma squared times the sum j from 0 to h minus 1 phi j squared. So what happens as we take h to infinity? Well, this just goes to the sum of, well, we're just going to sum the phi squareds from 0 to infinity. And I'm pretty sure we saw that earlier in the lecture. This is just kx at lag 0. It's the variance. The stationary variance, I guess, to be precise. So what does that mean? That means as we move far into the future, the best guess we have for prediction for our ARMA process is the mean. And what's the variance of our estimate? Well, it's just the variance of the process itself. Because as we move far into the future, our data that we've observed no longer has any direct relevance for prediction. Again, this is for a stationary ARMA process. That means that we are assuming that there is no trend. If we have an increasing trend, we could still assume that that increasing trend will continue. Again, sadly for maybe global temperatures. But if we have a stationary process, the mean is constant. It's not increasing, nor is it decreasing. That's why it's always our best predictor. It is what we would predict in the future. Also, I made a mistake here. This hat is supposed to be a tilde. I'm so used to just writing x hat and mu hat and everything because that's what we do in stats. But we're going to stop for today. But next time, what we need to do is we need to figure out, well, what happens if we don't have an infinite past for our data set, which is every data set we're ever going to look at, right? We need to, at least to the best of my knowledge, there isn't any that goes infinitely into the past, though it would be quite interesting if there were one. Regardless, what we're going to try to do is figure out how to replace the x tilde with the x hat. The same thought process that went into understanding x tilde goes into x hat, because as I mentioned, for a large data set, they're basically the same thing, because the piece that you're kind of throwing away, the x0, the x minus 1, are not really going to have much influence. But we still have to see what happens mathematically, and we will do that. But we will do that in the next lecture. So see you then.